So in this video, we're going to talk about phases and how particles and matter are arranged in a particular way that causes them to behave like a solid, a liquid, or a gas. And then most importantly, how the energy of that system causes it to change between a solid to a liquid to a gas and back and forth. So we've already really talked about matter and the three phases, but now we're talking about how energy has a much bigger role to determine what phase of matter is actually going to be present. So the most important thing to remember is that matter has three phases, solid, liquid, and gas, which we're going to talk about. But that phase or state, sometimes we'll often see it referred to both ways, is really determined solely by the arrangement of the particles. So how are the particles distributed and arranged for that particular phase? So gases, the arrangement of those particles are free form. So they're kind of spaced. Particles are spaced far apart, and they're random. So there's not some consistent pattern with a gas. If we have a balloon, the air inside that balloon is just mixed and moving about freely throughout the inside of that space. So in terms of movement, particles move freely, and they take the shape of their entire container. Take the shape of their container. Now, in terms of density, which again is how much matter is packed into that particular amount of space, gases are really lightweight. So gases are the least dense, and they're very easily squeezed together because of the amount of open space between the individual particles. So they're referred to as compressible. So when we drew particle pictures last semester, remember we always said that gases needed to be represented with a tail, but we draw them throughout the entirety of the box because they move about freely, taking the space of their container, and they've got a lot of open area, empty space between them. Right? For liquids, the particles are closer together, but their pattern is still very random. Okay, because liquids are free flowing, so they don't stay in one particular fixed pattern. And there's two motions that liquid particles go through that keep them constantly moving about. One is that all liquid particles move by vibrating and by spinning. So in a container of water, those water molecules down at the bottom of the container are constantly moving about, which is why they can help to form a solution so well, but they're not going up and down inside the can or inside the glass. They're just vibrating and spinning around the bottom of the container. In terms of density, we're going to loosely call it like a medium density. So liquids are definitely denser than gases, but they're not always denser than the solid phase. So they're kind of in the middle for the most part. Now, there are some examples where that's not true. And then liquids are not easily squeezed together. They're somewhat compressible, but they don't fit into a smaller amount of space just because you push on them. So remember, with liquids, we draw a liquid line, and then we have those particles kind of not connected, no particular pattern or arrangement. They're just kind of down at the bottom part of the container. And then the last phase we're just going to recap with are solids. For the arrangement, the particles are close together, very close together, and in a fixed pattern. So in terms of like a salt crystal, there's particular arrangement and kind of edges to those crystals because the particles are in such a aligned pattern. For solids, they still do have some mobility and they move just by vibrating. They have the greatest density, and again, they're not easily squeezed together because the particles are so closely patterned and packed together that there's not a lot of room to push those solid particles even closer together. Okay? So the reason that we're recapping the way that these three phases behave is that from the lab that we did the other day, we generated some kind of a temperature graph that showed these different regions that our temperature changed and then plateaued and then changed and plateaued again. And we're going to be using this graph as a representation of how energy caused a particular system to change. So now we're going to focus more on the actual energy of this particular unit. So energy is referred to as a force, and any force can cause change. So energy, a force that has the ability to cause change, and most importantly, is conserved. So in a particular closed system, there's not any additional energy gained or lost. So it very much mimics the law of conservation of matter. But in this instance, we're going to say the law of conservation of energy states that energy can neither be created or destroyed, only changed. Okay? So on this graph here, our x-axis is energy. So it's always going from left to right. Heat energy being added. And then our y-axis is in temperature. So at the lowest possible temperature, these particles are really closely aligned in a particular arrangement. At little energy added, all matter will start out as a solid. Right? And then as energy gets added, as we move along our x-axis, those solid particles increase in temperature. They start to vibrate more and more. And eventually they vibrate so much that they actually break their attraction to one another, and they go to a less patterned, still close together phase, which we call the liquid phase. And then eventually even more energy gets added and the temperature continues to rise, and those particles break even further away from each other. They start to vibrate and spin and move further away because they've got more energy. There's more energy in that system, to the point where they break their attraction even more and they turn into the highest phase energy, which is a gas. Right? I want to focus more on what these plateaus are telling us. We get these breaks in between. So what this is saying, from this point to this point, energy is being added, but the temperature isn't increasing. So what is changing here? If our temperature is staying constant from here to here, and energy causes a change, the point that's changing is the actual phase. So this is a moment where we see a phase change is actually occurring. And to go from left to right, or to go from a solid to a liquid, we refer to that phase change as melting. Okay? So down here under our phase changes, melting is when we go from a solid to a liquid. And it doesn't have to be ice. A lot of times you hear melting and you think just, well, ice cubes melt. If I take a solid bar of gold and I heat it up and turn it into a liquid state, I melted that bar of gold. Okay? It just requires a different temperature and a different amount of energy to do so. Right? So again, at that same plateau, but now at a higher temperature, energy is still being added, but our temperature is staying constant. So some change has to occur while energy is being added. So the change that's occurring from here to here is that we're going from a liquid to a gas, and we refer to that as evaporation. Okay, so evaporating is when we go from a liquid phase to a gas phase. So no matter where you go, from point zero all the way to the right, the energy is constantly increasing along the x-axis. But at certain points, from here to here, the increase in energy causes the solid to just increase in temperature. From here to here, the increase in energy doesn't cause the temperature to change, but it causes the phase to change. So no matter what, energy causes a change, always. And then the arrows going backwards are what would happen if energy gets removed. So if I take energy out of a liquid and we hit a certain temperature where that extreme occurs, to go from a liquid or from a gas back to a liquid, we refer to that as condensation. And if I go from a liquid back to a solid by taking energy out going this direction, we refer to that as freezing. Okay, so condensing or condensation is when you go from the gas phase back to the liquid phase, and then freezing is when you go from the liquid phase back to the solid phase. And again, freezing always implies cold. Most people always think of water freezing into ice, but if I take any liquid and turn it into a solid, that's freezing. What I'm doing is freezing the particles in a fixed pattern, which is why we call it freezing, not because it's cold. It just kind of sounds like it should be cold. And it's important to note that temperature does not change during a phase change. Super important. So during our phase change plateaus here and here, the temperature, our y-axis value, stays constant. So while something is melting, it's not warming up. The energy is causing it to just change from a solid to a liquid. Okay? So just a quick recap, because we'll be referencing these particle pictures and arrangements to help rationalize these changes. If we draw a particle picture before and after of freezing water to ice, initially we need it to start as a liquid, and then we're taking energy out by causing those particles to come close together and go into a lower phase energy state, which is a solid. Right? If we go the opposite way and we evaporate liquid water into steam, we're going to start with the liquid, but then we're adding energy, moving those particles apart, causing it to go to a higher energy system or a higher energy phase, which is a gas.